It's from the May 2016 examination, paper 1, question 9. Give it a try, and then hit play. So it's asking what's polar or nonpolar, which means we are going to have to draw the Lewis diagrams. Which means we need to do a little bit of accounting with each one. So OF2, I'm just going to highlight where these are on here. OF2, NH3, BF3, and SO2. So those are all the elements that we're dealing with. We need to know how many valence electrons each of these have. And we learned a shortcut after we had done all of the electron configurations and we figured out how to reason through it. We've determined that there was a shortcut that we could take to identify how many valence electrons we had for a lot of the elements on the periodic table. This first column, the alkali metals, all had 1 valence electron. The second column, the alkaline earth metals, all had 2. We learned that because of the overlapping energy levels, these are variable in the D block. And then we get to 3, 4, 5, 6, 7, and 8, starting with the neon. Helium is just 2 because our first energy level is so small it can't hold more than 2. And so with those number of valence electrons in mind, we're going to do a little bit of accounting for each of these. So we'll take OF2 first. We have 1 oxygen and 2 fluorines. The oxygen, there's just 6 valence electrons. 2 times 7, because of where fluorine is, it's in the 7th, it's going to be a total of 14. So we're going to look at, we'll do for total, 6 plus 14, we get a total of 20 electrons that we need. We can also identify right away that the one that needs the most to get to the full octet is oxygen, so this is going to be in the center because it needs 2. The fluorines only need 1 each to get to the octet rule. So I'm going to put oxygen at the center, and I'm going to go 1, 2, 3, 4, 5, 6 valence electrons around it. I'm going to put a fluorine down here and 1 over here. 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6, 7. And I can see that I can share that 1 electron with that 1 electron. Draw 1 line to represent the sharing of 2 electrons. The same thing with this one. Now I need to do some accounting because I need to make sure that I meet my total number of electrons, which we said was 20, and I need to make sure that each species feels 8 electrons. So I can count first 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20. I meet my octet rule, so that, or my total rule, that's good. And then I'm going to look at each of these species individually. So I've got 2, 4, 6, 8. 2, 4, 6, 8. 2, 4, 6, 8. So each of them feel the effects of 2 electrons, so they are both, or 8 electrons, they're all good. Get those out of the way for now. Now I can think about shapes. My central atom right here is oxygen. It has 1, 2, 3, 4 electron clouds, so 4 ECs. Only 2 of them are bonds. That makes this a bent shape. And we see that we've got each of these bonds would have an electronegativity difference, but more than anything, I see this great amount of negative charge on this end of the molecule, so I can assume that my net dipole is more positive on this end, going to more negative where my unbonded electrons on the central atom are over there. And so this one would very much be polar because it has a dipole moment, so it's not a. I'm going to go through the next couple a little bit faster. Nitrogen has 5. Hydrogen, there's 3 of them. They each have 1. So we're going to look for a total of 8. There's my molecule of ammonia is what that is called. I'm going to look at my central atom here, which is nitrogen. It has 1, 2, 3, 4 electron clouds. 3 of them are bonds, and so this is trigonal pyramid. And it also has a net dipole because of this extra unbonded pair here, and also because the nitrogen is much more electronegative than each of the hydrogens. So I'm going to have more positive in the 3 dimensions this way to more negative that way. So that one would be a polar molecule. NH3 is not correct. BF3 is a special case. We talked about this one as being a special case. The boron is small. It's a small atom. It has 3 electrons. It can only go up to 6. So we've got, rather than the octet rule, we have the 6 rule when it comes to boron. In boron trifluoride. And that was one that you need to memorize as an exception to our general octet rule. Make this a little bit nicer. So, BF3, this boron is the central atom. It has 1, 2, 3 electron clouds. All 3 are bonds. So we've got trigonal planar. And in trigonal planar, all of the electron clouds cancel out. Even though the fluorine is much more electronegative than the boron, they're all the same atom going out there. And so they end up canceling out in 3 dimensions. So it would be nonpolar overall. So that should be our answer. Let's do a double check with SO2. We've got, get my color here too, sulfur has 6. Oxygen, there's 2 of them, times 6. So we'll have a total of 18 electrons. We're going to put sulfur at the middle because there's only 1 of them compared to the 2 oxygens. We're going to have 1 double bond. We've got 2 unbonded electrons there, then 1 single bond. We can see we get a total of 2, 4, 6, 8, 10, 12, 14, 16, 18 total. Each of them feels 8, 2, 4, 6, 8, 2, 4, 6, 8, 2, 4, 6, 8. And the way that we could do that was with some dative bonds, which if you remember means that one of this species shares both of the electrons in the shared bond. So they're coming to the party and sharing all of their cookies. So this one, we've got 1, 2, 3 electron clouds. 2 of them are bonds. So we are bent overall. And we see this unbonded electron pair on the central atom means that we're going to be having a net dipole as well, which just proves that that one was polar.